Reactions of halogenoalkanes. Let us begin. So, before we start, what are halogenoalkanes? Anybody can let me know? What are they? Kind of in the name, but what are halogenoalkanes?
Alkanes that have a halogen attached to them via substitution.
Oh my. What a revolutionary concept, right? It's so interesting the fact that halogenoalkanes are alkanes that contain halogens. Crazy stuff, right? But that's what they are, right? Via substitution, right? Because we know that we looked at the reaction that creates halogenoalkanes, right? Which is substitution reactions, right? So that type of substitution and the mechanism for it would be what? What's the mechanism of the substitution that creates halogenoalkanes? Anybody?
From algene, sir.
No, from alkanes. Oh, sorry, I shouldn't mention that from alkanes. We're talking about substitution. Know that alkanes don't undergo substitution reactions. So, what type of substitution creates halogenoalkanes from regular alkanes?
I know about the electrophilic addition of an hydrogen halide.
Oh, but you didn't look at alkanes and how we can substitute the hydrogen with an halogen. Through,
That's possible.
yes, it is free radical substitution.
Oh yeah, yeah,
Yes, yes, yes.
sure. Yeah,
Free
yeah,
radical
yeah.
substitution. So, halogen alkanes are created via free radical substitution or electrophilic addition. All right. So, lesson objectives, right? So, we must be able to describe the hydrolysis of primary and tertiary halogen alkanes. We must be able to describe nucleophilic substitution, and we must be able to describe mechanisms involved in hydrolysis of primary and tertiary halogen alkanes. Right. That's what you must understand. But I'm including elimination, not the process of elimination, right? But what elimination is, right? The elimination reaction, right? So what are they? Halogens, otherwise known as alkyl halides, are a group of chemical compounds comprised of an alkane with one or more of the hydrogens replaced by a halogen atom. All right. So the halogen atom, fluorine, chlorine, bromine, iodine. Right. I don't think I've ever seen astatine, right? But those general halogens that we look at. So the characteristic of the CX bond, X usually marks the spot, right, for halogens, right? So we usually use X to denote halogens. With respect to electronegativity, halogens are more electronegative than carbons. Wow, how revolutionary. This results in a carbon-halogen bond that is polarized. As shown in the image below, a carbon atom has a partial positive charge, while the halogen has a partially negative charge. Everybody understands this?
Sarah, could you explain it?
Explain it. Interesting. All right, so
Yeah.
we have a carbon here. Let's give me a random halogen.
Chlorine.
Chlorine. All right. So chlorine's electronegativity is larger than carbon. And what is electronegativity, by the way? What is electronegativity?
Uh, the ability to pull electrons closer to you or to attract electrons.
Wonderful. The tendency for a species to attract electrons, to drag the electrons in bonds and in lone pairs towards itself, right? So it drags the electrons toward itself. So let's say that there were, well, in every double bond, we know that there are two electrons, right? So let's say the two electrons exist like this, right? Over a period of time, the chlorine will attract the two electrons closer to itself. And the electron's density, or the electron density is more dense on chlorine, it's going to attract a slightly negative charge, while the electron-less carbon will attract a slightly positive charge. Hence, the bond we have here is polar, and that is the dipole arrow that we have there. Make sense?
Yes, sir. Okay, good.
Lovely. All right. Remember, I know it's a second topic in Module 1, Unit 1 Chemistry, forces of attraction. All right. So this is it. So this is understanding the polarity in the bond, right? Shanique, is there something else you want me to repeat, or is that good now? Shanique asked me to repeat something in the chat. Everything is good? All right, good. It's good enough. All right, so let me know if it falls out along the way. So electronegativity differences, right? The electronegativity differences. So the following image shows the relationship between the halogens and the electronegativity. Notice as we move up the periodic table from iodine to fluorine, electronegativity increases. No, I don't want to bore you guys because you've done this time and time again. Module 3, Unit 1 chemistry. Right? For persons who didn't do it, then this is the trend. Right? But for everybody else, everybody understands this already. Electronegativity increases as we go up the groups and across the periods, periodic trends, right? So that is how it influences it, right? It also increases the inductive effect across a molecule, right? Because the more electronegativity or the more electronegative a substance is or a atom is, the higher its tendency to attract electrons. So it may drag its electrons away from an area and allow that area to be charge deficient and allow that area to gain more concentrated charge. But we're going to look at how that works in the acidity and basicity of organic compounds, right? Really important. The relationships between bond length and bond strength and molecular size as well is important in understanding these things. So as we progress down the periodic table from fluorine to iodine, molecular size increases. Also something we looked at in Unit 1 chemistry, right? The atomic radius increases as we go down the groups and across the periods, right? Also, the bond length increases. So bond length will increase, right? Because the atomic radius of the halogen increases, right? And the longer the bond, the weaker the bond strength. Unit 1 chemistry, right? So it's there as well. Actually, the fourth topic in Unit 1 chemistry, module 1. Right? So these things exist. We've looked at them before, time and time again. Right? So it's just an important relationship to look at. All right? And we will be looking at relationships like these going forward in chemistry. All right? So the physical properties, no, the solubility of halogenoalkanes, right? The carbon to halogen bond is polar, as we spoke about, but non-polar enough to be soluble in water. So it's really, really polar, but it's not polar enough to be soluble in water. So halogenoalkanes are soluble in organic solvents and insoluble in water, right? So organic solvents like toluene, right, which is I mean, I think you guys would know what toluene, right? Methylbenzene, right? And also in substances like ethanol, those type of things, right? So classifying halogenoalkanes now. Halogenoalkanes have the general formula CnH2n plus 1x, right? Or we can write R dash X, right? Where X is a halogen. They may be classified according to the position of the halogen functional group in a similar way to alcohols. So we looked at alcohols before. So primary halogenoalkanes are attached to a carbon which is only attached to another carbon, one other carbon, right? So in this case, it's only one other carbon. Secondary halogenoalkanes are attached to a carbon which is attached to two other carbons. And tertiary halogenoalkanes, right? We would have the halogen attached to a carbon that is attached to three other carbons. Everybody's fine with this information? Drop a one in the chat if everything is fine. Go ahead. Somebody unmuted.
Yeah, said we're fine.
Okay, lovely. All right. So let me know if everything is fine, or let me know if there are any issues. All right. So can I see some ones in the chat if we're ready to move on, if everything is fine, if the information is good. If you're not getting something, please ask and not sit and let it marinate. All right. So we have that here. So classified halogenoalkanes now, primary, secondary, tertiary. Now let's look at these reactions, right? We have to understand the reaction mechanism of nucleophilic substitution, right? A nucleophile is a reagent that donates a pair of electrons, right? And in that case, it is a Lewis what? Is it a Lewis acid or a Lewis base? If you donate a pair of electrons, are you a Lewis acid or a Lewis base? spoke about this in the reactions of alkenes.
Repeat the question, sir. If you want electrons,
If you donate a pair of electrons, are you a Lewis acid or a Lewis base?
your lowest base.
Lewis base if you donate. All right, that's interesting. So the Lewis acid is electron acceptor and the Lewis base is electron donator. Lovely, right? So we have that. So a new covalent bond tends to be formed right there, and you know that type of covalent bond is called coordinate covalent bonding, right? So we have some examples of some type of nucleophilic substitutions here, right, that you guys can look at, right? But we're gonna look at it specifically with our halogen alkanes. So let's look at this, right? Nucleophiles are either negatively charged ions or atoms with a partial negative charge, right? So examples are the hydroxide ion, right? Ammonia, right? And we also have a cyanide complex with water, right? So we have that. And it's after the recording, I'm going to explain why cyanide kills. All right. So in a nucleophilic substitution reaction with halogens, the nucleophile replaces the halogen, right? So we're substituting. That's exactly what we mean, right? The carbon is electron deficient because the halogens are more electron negative, right? So if we look at something like this, the carbon will become more deficient because the halogens take the electrons away, right? They drag them closer. It's an inductive effect. We're going to have a positive inductive effect on the carbon, right? Because the electrons are moving away, right? So the electron pair movement is from the nucleophile to the electron deficient atom. So we're going to be looking at that. And a bond is formed between the nucleophile and the electron deficient carbon atom, right? A bond is broken between the electron deficient carbon atom and the halogen, and a double-headed arrow is always shown for this, right? Because there's always a movement of two electrons, right? So as it's saying here, the nucleophile here, right? Let me start off with this. So this species here, we know that the halogen is more negative than the alkyl group because halogen is more electronegative, right? So there's going to be a donation of electrons towards the alkyl group there, right? Pushing the electrons away and creating a heterolytic cleavage, right? Creating a bond between the nucleophile and the alkyl group and which is in substitution of the halide, right? So you're gonna have the halide ion out there like that. So this is the mechanism, This is all of what the mechanism is. There's nothing more to this mechanism. Are there any questions or concerns about this mechanism? Any issues? Everything is fine? Kinda expecting an answer.
Yes, sir. Everything is okay.
All right. Okay. It seems so. All right. I'm not hearing any questions, so everything seems like it's fine. All right. So that's the mechanism there. You think so, Gabriel? Are there any issues? Do you have a question to ask?
That's the thing. I have a question. I don't know if I just need time for it to just settle a little bit in my brain.
All right.
Um,
So as we go on, if getting darker, just let me know, all right, and see if you can compose a question while we're going through. All right. So the hydrolysis of halogenoalkanes, chromo, bromo, and iodoalkane hydrolysis. The rate of hydrolysis. So the reactions are similar in each case. The rate of hydrolysis is related to the bond strength of carbon halogen bonds, right? So notice as we go down the group, there's a faster rate of hydrolysis by hydroxide ions, right? And there's a weaker bond energy between the carbon and halogen bond, and that makes sense. All right. So if we react the halogenoalkanes with hydroxide with basic solutions, they will hydrolyze, right? In a sense, in this specific reaction rate gradient, right? So what we're saying is that this will be more likely to hydrolyze than this, which is more which is more likely to hydrolyze than this, which is more likely than this. All right. So that's the hydrolysis really. We haven't really, we're not going to really look at the, we're going to be looking at it actually, in a mechanistic framework. But since you guys already know the periodic trends, because you should have done unit one, so you did know the periodic trends of the halogens, so you'd understand why this is happening, right? I remember if you have a question you just asked. So we're going to be looking at that in a way. I'm going to use something to explain this. Substitution in primary halogenoalkanes, right? So this is what's happening. So primary halogenoalkanes react with aqueous hydroxide ions in a 50 to 50 ratio of ethanol, right, with water. Why we use ethanol and water is because halogen alkanes are not soluble in water by itself. So you have to make a mixture, right, with something that is with an organic solvent in order to, allow it to dissolve, right, allow it to react, right? So with the water, we're getting our hydroxide ions from that, and the ethanol is our solvent that we use to dissolve the thing, right? So the reaction, so this reaction only occurs where the two layers meet, right? Because we know that ethanol and water will not mix, right? So we have um ethanol. Let me just write it like this. So we're gonna have H2O, and we're gonna have C2H would be 2N plus. That would be 4. That would be 5OH, right? That would be 5OH. 1, 2, 3, 4, 5. Yeah. Okay, so that is it. So they're not going to mix. So the reaction occurs when they actually touch. All right. So we're gonna have this type of reaction occurring. So looking at something like this, right? So this ethane, right, reacting with sodium hydroxide to give a substituted, so to give an alcohol, a primary alcohol, right, and a sodium bromide, a metal halide, right? So that is what's happening here. So the primary halogen alkanes will react with water to form primary alcohols, right? So the secondary one will react to give secondary alcohols. The tertiary ones will react to give tertiary alcohols. So we're seeing how we can create these alcohols that we discussed before, all right? So looking at that, so the hydrolysis of water is slower with the hydroxide ions because water is a less effective nucleophile. So water is not really a good nucleophile, right? But we can do it with water and not hydroxide ions, all right? So we're going to be looking at that next. But before we go, is everything fine? Everything fine so far? It's just a substitution reaction. We just swap this for this. All right, so they just switch places. That's what we get. Everything fine so far. All right, so we have that there. So this is happening with the OH ion, but if we use water, it can be really, it can be, it's going to be less effective, right? But it's going to be effective nonetheless. All right, so let's look at this though. Before we get into that, we can look at SN2 and SN1 reactions, because this is where we're going to actually look at this. All right, so SN1 and SN2 reactions are two different types of substitution reactions that are nucleophilic in nature. All right, so we're looking at the major types of substitutions that we have here. All right, so let's look at this. SN1 versus SN2 reaction. So the class of halogen alkanes that undergo both, right? So SN1 reactions, right, occur in tertiary halogenoalkanes, right? And SN2 reactions occur in primary halogenoalkanes. The number of steps now, right? The secondary halogenoalkanes can react by either SN1 or SN2 mechanisms, by the way, right? That's interesting. Here we have now the transition states now. So let's look at this. The transition states, right, or reaction intermediate. So a reaction intermediate, a carbocation intermediate is created in SN1 reactions, while a transition state is created or is realized within SN2 reactions. The type of solvent for SN1 reactions are polar protic. Type of solvent for SN2 is polar aprotic. And then we see the type of bond fission. Both of them are heterolytic because we have a more electronegative species. And we're going to look at that, right? So this is just a summary of both of them. So SN2, two species are involved. That's why it's an SN2 reaction. two species involved in the formation of a transition state. The reaction is called bimolecular nucleophilic substitution, or we just call it SN2. Right? Bimolecular because there are two molecules. The mechanism for primary halogenoalkane hydrolysis is called the SN2, right? Or the substitution nucleophilic, right, second order reactions. That is what it's called, right? So the rate determining step involves two species, right? So the halogenoalkane and the hydroxide ion, and the rate reaction here is given by the halogenoalkane and the nucleophile concentrations, right? They are second order, all right? But we're not going to get into the second order or whatever, all right? So the rate equation is there, all right? We have what SN2 means, and we know that primary halogenoalkanes undergo SN2 reactions, right? SN1 now is different, all right? Only one species is involved in the formation of a transition state, or we call that an intermediate, right, in a sense, all right? The reaction is called unimolecular nucleophilic substitution, or the SN1 reaction, right? And tertiary amine halogenoalkane hydrolysis undergoes this substitution reaction, this nucleophilic substitution reaction at the first order, and the rate is determined only by the concentration of halogenoalkanes present. All right. Tertiary halogenoalkanes produce the more stable tertiary carbocation, right? Hence, they undergo SN1 reactions. All right. So that's the difference between the two. Okay. Let's look at what it's talking about. So SN2 now, right? We know that SN2 only has one thing. Well, in this case, we'd have two, right? But it has the creation of a transition state. All right. So the ethanol is primarily used as a solvent because halogenoalkanes are not going to mix with aqueous solutions. And the mechanism for the reaction of chloroethene and hydroxide ions is shown below. So the overall reaction, we're going to have hydroxide ions present in solution. And we're going to have that replacing the chlorine to give the ethanol, all right? And we're going to get the chloride ions like that. So we're going to have this type of mechanism. This is an SN2 type of mechanism, all right? The creation of a transition state. So let's have a look at what's happening here. All right, so let me create a different slide after this, and we'll go through it. Everybody following so far? Let me just check the chat. All right. The screen is blank. Yeah, the screen should be blank. So everybody's following so far. Just let me know. Drop a one in the chat if you're following so far. We're gonna be going through this mechanism, all right? So first, we're going to start off with the chloroethane. The chloro, the well, the yeah, the chloro ethane, right? So the chloromethane, actually, by the way, it's chloromethane we're dealing with. So we're gonna have carbon right there bonded to different molecules. So we're gonna have something like this. One hydrogen there, one hydrogen there, one hydrogen there, and one chlorine there. All right. So that is fine. All right. What's going to happen here now, right, is the creation of this type of interaction with hydroxide. All right. So we're gonna have hydroxide over here. Let me just put the electrons on the hydroxide so you know that it is a nucleophile, right? So what we're gonna have here now, right? Before we look at the interaction here, we know that the chlorine is going to be more electronegative, right? Creating a slightly negative charge here, slightly positive charge here, right? Slightly negative charge, slightly positive charge, right? Everything is understood there. What's going to happen here now is that the large the large structure of chlorine specifically, or the large negative charge on chlorine, will cause the molecule to actually shift and look something like this. All right. So usually you're going to see the reaction looking something like this. All right. So we're gonna have the molecule looking something like this. Let me remove those arrows. So let's look at the movement of the electrons now. The carbon is slightly positive as we know already. So therefore the electrons are going to be attracted. So the electrons are going to be moving, right, towards the carbon there, right? And then we're going to have the formation of a transition state, right? So it's not that it's going to break, the bond is not going to break, all right? We want to see this happening. There's there's going to be a breakage, but it's not going to break just yet. What we're going to have is the creation of a transition state. And let's look at what happens here. Within this type of reaction, right, it's only one step. So we're not going to have a intermediate that it reacts with, right, in order to, have that type of reaction. So everything happens at once. So while the chlorine is leaving, right, the hydroxide is coming in, right? And this is a transition state. All right. So we have this transition state being the product here. All right. So all of this is one step, we're just showing the creation of a transition state, right? So from what we explained already to this. Everybody's fine so far?
Circle this back one more time. One more time.
All right, one more time. So let's get this understood. All right. So we're going to have our halogenoalkane, right? We understand the polarity in the bond, right? The polarity will give us something like this, slightly negative, slightly positive. And the slightly positive charge on the carbon is what is going to attract our nucleophile, right? So that slightly positive charge is what a nucleophile loves. A nucleophile loves the positive charge, and it's going to donate two of its electrons to carbon, right? And it will do this in a transition state. So while the hydroxide is coming in, the chlorine is moving out. So that's where we get something called a leaving group, right? So it's a leaving group. So the chlorine is leaving. So what we're saying, is that as the hydroxide ion gets closer and closer to the carbon to actually form that bond, right? The chlorine is getting the bond length between the chlorine and carbon is getting longer and longer, right? So what's happening here is that there's going to be no carbocation intermediate at all, at all, at all, at all, right? We're just going to have one concerted reaction. Everything happens at once. As one group come in, the other one leave same time, all right? So we're going to have that happening, and there is what we're going to have from this is going to be the original that we had before. We're going to have something that looks like this now, all right? Showing the wedge model, it's going to look like this, right? Obviously plus the chloride, all right? So the chloride there plus that chloride ion, all right? So this is step one up here. Well, all of it is one step. Let me not say that. This is all one step, all right? It's one step, but let's say that the part A is up here. Part A, we have to show, right, the polarity of the bond and the nucleophile's attraction into the entire molecule. Part B, we're showing the transition state, and part C, we're showing the product. But it is all one step. Do not mistake it. All right. Any questions about this?
No, sir. Thank you.
All right. So that is what the SN2 reaction is about, right? So that it can either happen like this. Give me one moment, please. Give me one moment, please. One moment, one moment, one moment, one moment. Mm-mm-mm-mm. All right, so we have that reaction there. All right, so let's look at this. All right, so moving on to SN1, actually. Not gonna look at that yet, but let's look at SN1. All right, so with SN1 types of reactions, it's going to be a little bit different. With SN1 now we have the formation of the intermediate, right? So tertiary halogenalkanes are the ones that undergo this. So note that we had a primary halogenalkane for this, but now we have a tertiary halogenalkane, all right? So now we're going to have the creation of an intermediate, and this is because tertiary halogenalkanes will produce tertiary carbocations which are stable. So it is stable enough to exist by itself, so an intermediate can be formed. With SN2 now, the primary halogen alkane is not going to do it. It's not going to exist. It's not going to freely exist in solution. So the reaction happens at once, in one step, one go, right? But within this reaction now, we're going to have a slow step creating the carbocation intermediate. Because everybody knows that when we create an intermediate, it is a slow step and it is our rate determining step, right? Did that in unit one, all right? And then we have a fast step where the nucleophile now attaches, all right? So it's a two-step mechanism now. The carbon, hopefully we're seeing it, right? So we're going to have this now. The slow step is the halogen leaving the group. So we're gonna have that unimolecular type of thing, right? So we have that unimolecular reaction, that first step, where the carbon in this case the carbon chlorine bond breaks heterolytically, right? And that chlorine atom will actually be ejected as a chloride, right? And we're seeing the formation of this group. So notice there's nothing affecting it, it's unimolecular. SN1, unimolecular, right? Nothing is affecting it. It leaves by itself. So it's a slow process, right? Creation of the intermediate. That is the first step. And then the second step now is the addition of the nucleophile, right? So now the nucleophile can go in when the intermediate is created and we have that tertiary alcohol being created, right? And that is the fast step. So the first step, which is the creation of the carbon-cation intermediate unimolecularly, that is slow. And the second step is the addition of the nucleophile, which is fast, right? So this is the substitution reaction that occurs in tertiary halogenoalkanes, which is the SN1, right? So what we're gonna understand here now, the reason why it's a slow process is because of steric hindrance, right? So it's difficult for the incoming group to react due to the bulky CH3 groups, right? So this occurs in tertiary alkanes in this type of sense because it's really bulky, right? So it's not going to be easy for a nucleophile to attach like that and undergo SN2. It's not going to be possible because of steric hindrance, right? And then also the positive induction, stabilization of the carbocation. So if you can't go through an SN2 reaction, but you have a carbocation intermediate that is free, then we're going to form the carbocation intermediate, which is free and stable, and then we're going to add our nucleophile after in the second step. All right. So that's really SN1. Are there any issues with SN1? Any issues at all with SN1? Any issues? All right. Seems like everything is fine so far with that. All right. So substitution or elimination. When halogenalkanes undergo reactions with bases, nucleophilic substitution and or elimination reactions can occur. Must be basic, alright? When halogenalkanes react with strong bases such as an hydroxide anion, right, a mixture of both products is usually formed, right? So elimination product and substitution product. The major product depends on the reaction condition and the structure of the molecule. right? So this is just giving you what elimination is. The syllabus doesn't require you to understand elimination through and through, right? But it requires you to understand that primary undergoes substitution, secondary undergoes, well, primary undergoes SN2, right? Tertiary undergoes SN1, and secondary itself can undergo both SN2 and SN1 and elimination type reactions. So eliminations exist, right? And that is how it really works. Okay, so this is just a little brief slide speaking about elimination. All right, and then this is showing how elimination can happen. All right, but I notice that your syllabus don't ask you to really look into it, but this is information just in case you want to understand how elimination mechanisms work in secondary halogen alkanes. All right, and they will produce alkenes by the way water and the halide. All right, so that is it. All right, so you're gonna have dehydrohalogenation. All right, it is a dehydrohalogenation. All right, that is what happens to the elimination. All right, so we'll have an activity here to describe the mechanism for the hydrolysis of a named primary halogenoalkane and a named tertiary halogenoalkane. All right, so I'm going to ask you guys to provide with a mechanism. All right. Give me a moment. Let me just guess. Okay, I'm not gonna guess. Let me create the thing. So let's see. CH3, CH2, CH3, CH2, BR, 1, 2, 3, 4. All right. So working with that then. I want you guys to show the hydrolysis, right? With which is through SN1 or SN2 substitution of CH3, CH2, Br, right? For your primary, right? And for your tertiary, right? It would be CH3, CH2. What should be your tertiary? Mm-mm. What do you think should be the tertiary? Let me put the Br here. All right, so let me just put CH 3 to Br. All right, let's work with that. So hopefully you guys are able to just do those, all right? And you guys have a little bit less than 15 minutes to just prepare these two mechanisms, right? So just write out what your reaction is going to be, what reacts with what to give what. And then after you see your reaction and you know what you're going to get, then you write a mechanism. So I want you guys to provide the mechanisms for these. Okay? Is everybody fine with that? Hello, is everyone fine with that? All right. So I'm going to give you guys 5 minutes, all right, to just try to work out the mechanisms for those, right? 5 minutes. And within those 5 minutes, if there are any questions, just let me know, all right? The 5 minutes starts now. Just try to get a pencil and a piece of paper and you work with your mechanism. Because you learn best by actually doing it. So I gave you two halogen alkanes. And by the way, I want you to name them. Name your product and name your reactant. Alright? And you do your thing. Okay, so write out your overall reaction. And your overall reaction should include your conditions, right? Your solvent, because it's not aqueous, we can't assume, so we have to write our solvent and give us our product. And then you just write your mechanism. Alright? So I'll be here if there are any questions. And that's, let me just check something real quick. And the summary is just after, so that will be it. Alright? So go ahead.